Hello and welcome to this new video. In this video, I'm going to solve exercises 1 through 4 of chapter 2. I hope that you tried at least to do them on your own. The first one, we did something similar in class. Compute the integral of Ez over gamma, where gamma is given by this formula. Now, it's not really necessary to draw this curve, but at any rate, I drew it here. So it's a kind of spiral asteroid, okay? So it looks like something we already did with ET here, okay? But it's a little bit different, okay? So this path joins the point 0, 0, when t equals 0, to the point 4 pi square 0, when t equal to pi. Okay, if you try to do a direct computation, you will get a horrible integral, and it's not computable actually. Okay, because you get, so unlike a previous one, we get the ET square cosine cube, and this is not computable actually in the usual way. So we have to think of another way of computing integrals. Now we know 3 ways of computing integrals: the direct method, Barrow's rule if it's applicable, and Goursat-Cauchy theorem. Okay, and we shall learn 2 more in the next section. So, well, does e to the z possess an antiderivative? Yes, itself. Because the exponential of z is given by this power series about 0, and the radius of convergence is infinity. Okay? So this is the fundamental result, and actually you can take it as a definition, okay, of the exponential function. Since the radius is infinity, it means that, so we have absolute convergence, and we have uniform convergence on compact subsets of C. This is important actually, because power series are uniformly convergent when we are on every compact subset of the disk of convergence. Okay, so this is an important result that you shall use later. So this is the exponential, and therefore if you don't know or don't remember the exponential, when you differentiate term by term, because it's a convergent power series, you will get Ez actually, you get the same thing. So it means what? It means that e to the z is its own antiderivative. Okay. Now, of course, if I had e to z, then the antiderivative would be e to z over 2. Okay. So I hope you know these results, but they are straightforward. If you take this as a definition, just differentiate term by term, you get the derivative is equal of Ez is equal to Ez. Okay, because the derivative here we have 1, here we have z, and so on. And therefore we can apply Barrow's rule. That tells me that the integral is e to the z evaluated between the endpoints of the path. And now we already observed that gamma of 0 equals 0 and gamma of 2 pi equal 4 pi squared. Okay, because the sine vanishes at 0 and at 2 pi, and the cosine is equal to 1. So this is just e 4 pi squared minus 1. Okay. So this concludes the first exercise. Second one. Okay, so recall that the integral from minus infinity to infinity of e minus x squared equal radical pi. This is a result that you probably proved several times. So we will use it to compute these integrals, the integral from 0 to infinity of cosine t squared and the same for sine t squared, using complex variables methods. So here's the approach. So consider a positive number r, which will let tend to infinity. And let gamma be the loop composed of the straight line segment 0 r of the real axis, the arc re to the it, t between 0. So this is a 1/8 of a circle, okay? And finally, the straight line segment joining ei pi over 4r to 0, 0, okay? So first a figure. So this is the straight line segment from 0 to r, and then we do a 45 degrees of rotation along the circle of radius r, and then we go back to 0. Okay, so this is a typical path of integration. Okay, so we have to integrate now the function e to the iz square along gamma, and then let r tend to infinity. So the strategy is actually to compute the integral in two ways. Okay, so first we use some theorem like Barrow's rule or something, or Cauchy's theorem or Cauchy's formula to evaluate the integral by means of complex variables method, so by means of the results of the theory. And then we try to evaluate it directly, so integrate along this path that I call gamma 1, then gamma 2, then gamma 3. So capital gamma is the composition of gamma 1, gamma 2, and gamma 3. So we'll try to evaluate at least the integral along each path, and then let r tend to infinity and see what happens. Okay, so we have, in short, we'll have the strategy is to compute in two ways the integral. Okay, so one way by the results of holomorphic functions, about holomorphic functions, and the second way, which is more computational, is by going back to the definition. Now we don't need to integrate exactly. For example, in gamma 2, we cannot compute exactly, but we have an estimate of what happens to this integral when r tends to infinity. Okay, so this one is computable. The integral over gamma 1 is computable. Well, not total. Well, it depends what you mean by computable, but we'll see actually. So, so let us begin with the first method of computing the integral. E to the iz squared is holomorphic on the convex set C. Okay, so the domain of holomorphy is convex. So, and we know by a theorem of section 2.1 that e to the iz squared possesses an antiderivative, right? Or equivalently, the integral over any loop is 0. Okay, these two are equivalent. So if you use Barrow's, if e to the iz has an antiderivative, then the integral is 0 by Barrow's rule, and we proved actually the converse, that if the integral over any loop is 0, then it has an antiderivative. So this is, I think, theorem 2.1. Okay. So note that once again, in order to justify our computations, we need to be precise. So there's a condition on the function, which is to be holomorphic, and there's a condition, geometric or topological, on the set where f is holomorphic. Okay, when the set is C, C is everything, so you don't need to worry about anything. So, okay, so the integral is 0 by our theorems. Okay, so now let us try to estimate the integral along the curve. So first, let's start with the first straight line segment. So a straightforward parameterization would be gamma 1 of t equal t, t between 0 and r, right? This is the straight, so we are joining 0 to r. Okay. So, but we need the derivative, so the gamma 1 prime is 1. Okay. Now, once again, we don't need to write the formula for the composition, actually, which is cumbersome. But what we use is, we write now the integral over gamma is the sum of the integrals over each part, and each part has a straightforward parameterization. Okay, so this is what we do in practice. So don't worry about the formula for the composition. So now gamma 2 is, of course, a part of the circle. So the radius is r, and the angle is between 0 and pi over 4, okay, because it's 45 degrees rotation. So So this is straight. This is a classical result, so you should know it. So, or we can write it as r cosine t plus r plus I ir sine t, if you like. Okay, but this is fundamental. So these two are really fundamental to know. The parameterization of a straight line segment joining 2 points, and the parameterization of a part of a circle, of an arc of a circle. Okay, if I had half of a circle, I would have t between 0 and pi. If I had to integrate along the full circle, then t would be between 0 and 2 pi. Okay, so now for gamma 3, so of course we can find the derivative because it's important. When we evaluate, we put f of gamma t and multiply by gamma prime. Now for the third path, on the first bisector actually, it joins r ei pi over 4 to 0. Now there are many ways of writing down a parameterization of this straight line segment, but we have to pay attention to the orientation, okay? Because otherwise you get wrong results. So here it's a straight line segment. So when t equal r, we are at r ei pi over 4, which is, by the way, 1 plus I over radical 2, because cosine pi over 4 is 1 over radical 2, and same for sine. So we can write in this way. This is perfectly acceptable because, so we cannot write t between r and 0, okay, because r is positive, but we can use this notation that tells me about the orientation, okay? So when t equal r, we are at r ei power 4, and when t equals 0 at 0, okay? So this is one way that I find very convenient. So of course we can find the derivative, just it's a linear map. But this is not the only way. We can write r minus t between 0 and r, right? When t equals 0, we're at r ei pi over 4, and when t equals r, we're at 0. Okay, so this is the opposite, actually. This path is the opposite of this path if we take the orientation from 0 to r, okay? So we already encountered these things. This is actually by definition, if you like. So the path inverse to gamma is gamma of a plus b, or alpha plus beta minus t, right? Okay, so now here we don't, so okay, of course we can write t from 0 to r, but this is also acceptable. So we can find the derivative, but look now, so one has to be consistent, of course. So the derivative, because we have minus t, is minus this constant. Okay, so here when we integrate, we get the integral from r to 0. This is what I mean by this. Okay, and here is the integral from 0 to r, but with an opposite derivative. So we get precisely the same result. And there is a third way. Because as I told you, every path can be defined on 0, 1 by a change of variables. So instead of r minus t, I put 1 minus tr. So once again, when t equals 0, we are at r ei pi over 4, and when t equals 1, we are at 0. So this is just decreasing. This function is decreasing linearly from r ei pi over 4 to 0. Okay, so this is a little bit sophisticated way, but it's also acceptable. So we will find the derivative and pay attention. The derivative is not the same here. I use the same symbol for gamma, but you choose one of them. You are not obliged to use them all. Okay, so note that you have the same sign here, but with the constant r. Okay, so now we shall see that when we integrate, if you use this parameterization or this, we'll find exactly the same result. Okay, so now I know that, so the direct way tells me that the integral over the loop is the sum of the integral over each piece. And now I have a parameterization of it. So let us try to estimate at least by a direct computation each one. Okay, the first one, straightforward. So I just replace f of gamma t times gamma prime. Gamma prime is 1. Gamma is t squared. Gamma of t is equal t. So I get the integral from 0 to r of ei t squared. And that I split into a real and imaginary part. Okay, now the purpose of the exercise is to compute these integral when r tends to infinity. By the way, these are not computable in terms of known functions, so we have to introduce new functions to compute them. Okay, so the usual methods of integration that you learn do not work here. Okay, so we have to introduce a new function. But so I do nothing actually. I leave them, and I know that when r tends to infinity, they tend to the values I need to compute. Okay, so I don't touch them now. Now, for the third one, for the third integral, if you use the first parameterization, which is t ei pi over 4, and once again pay attention to the orientation. If I use this orientation, I have to specify that t varies from r to 0 in this way. So the integral is from r to 0 and not from 0 to r. Okay, so this is a convenient way. This is a method that I find very simple. Okay, so, and now when we raise to the power 2, we get t squared ei pi over 2, because ei pi over 4 to the power 2 is ei pi over 4 times 2. Okay. And now ei pi over 2 is just I, as you may check, because cosine pi over 2 is 0 and sine pi over 2 is 1. So this is I. I times I is minus 1. Now the ei pi over 4 is a constant, which is 1 plus I over radical 2. So I put it outside. And there's a dt here. And therefore I get the 1 plus I over radical 2 times the integral from r to 0 of exponential of minus t squared dt. So just direct evaluation. Now, once again, if you just use the elementary functions that you know from first year, you cannot compute this integral. So you have to introduce a new function, for example, the error function, if you like. This integral is related to the error function. Okay, so we do nothing actually, but when r tends, so first let us write it as the integral from 0 to r, so just put the minus sign here. And when r tends to infinity, this integral converges to radical pi over 2, because it's half of the, okay? So we do nothing here. Okay, so the first one converges to something I need. The third one converges as r tends to infinity to a constant that I know what it is. Now, what about the second gamma 2? And by the way, if you use the second parameterization, we should get the same result. Otherwise, there's an error. So if you use the second parameterization, r minus ti pi over 4, and do the same computation, so we get this. Now observe that we have the minus sign outside and the integral from 0 to r. So it's this constant times the integral of exponential of minus r minus t squared. Now, okay, don't try to expand this, right? Because it will lead you nowhere. But rather, if you do the change of variable s equal r minus t, then will be between 0 and r, same thing. Actually, the bounds do not change because the minus ds. So if you like, when you do the change of variables s equal r minus t, the 0 becomes r, the r becomes 0, and you have minus. So we get exactly the integral from 0 to r of e minus s squared ds. And once again, we get the same result, but instead of, we can also write e minus t squared dt, same thing. So this is another way of checking that. But we did an extra step by doing a change of variables. This is why I prefer the first method, which is more direct. Okay, but you have to pay attention to the orientation. Okay, so even if t is between 0 and r, we have to look at the orientation. Is it from 0 to r or from r to 0? Okay. Now I leave to you as an exercise to check that the third condition gives the same integral. Okay. Now for the second integral over gamma 2, we just replace gamma 2 is r e I t. So when I raise to the power 2 here, because that's square, I get I r2 e2 I t times the derivative. Now we compute this, we split into the real and imaginary parts. So this gives me e cosine, so cosine to t, I put the constant outside, plus I sine to t. but because the I is outside, so the real part becomes imaginary and get minus. So if you do the algebra, you get this formula. Why did we do that? Because now we have an exponential of a complex number written in usual way, real part, imaginary part. Now, the imaginary part doesn't take any role, because when you take the modulus, you get 1. So this is what determines the conversions to 0, actually, this real part. But this is not straightforward, so we have to do something. Okay, so the first thing is to split into real and imaginary part. This is straightforward. And now we take the modulus. The modulus of this guy is equal to the modulus of this constant, which is r, times the modulus of this integral. Now, once again, the modulus of the integral is less than the integral of the modulus. The integral of what is inside is the exponential of the real part, because the modulus of the imaginary part is 1, as you know. So e to the iy has norm 1, as you may know, because it's cosine y plus I sine y. Okay, so these are, I hope you already encountered these kind of things in a previous course. Otherwise, you will have to review the properties of the exponential. It doesn't matter how did you define it, actually. It's important that you remember the properties of the exponential. Okay, so the modulus of all this, the modulus of EIT is 1. The modulus of this exponential is e to the minus r squared sine 2t, right? And now we are almost done, but we have so if I didn't have the sine 2t, then this would be straightforward, because this is just exponential of minus r2 tends to 0 and wins the race against r, actually. But I have this sine 2t that vanishes at 0, and I get exponential of 0, which is 1. So there is a small problem, but it's easily solved by recalling a convexity inequality about sine. I hope that you already know this inequality. Sine theta is bigger than 2 over pi theta for theta between 0 and pi over 2. And there are many ways to prove that. You can just make the difference, do the variation, and this is something that you should know to do. Another way is geometric. So just draw the graph of sine, which is concave. Since it's concave, then it's above its chord, joining 0 to pi over 2, 1. So this is the equation of the chord. Okay, joining the endpoints of the graph, and this is the graph. So we are saying that sine is above its chord. This is concavity. Okay, anyway, so this is a fundamental inequality to know, but of course we have to restrict between 0 and pi over 2, otherwise the result is wrong. Okay, because if theta is big, this tends to infinity, whereas this is bounded. Okay, so pay attention to the domain of validity of this inequality. And having said this, so if t is between 0 and pi over 4, then 2t is between 0 and pi over 2. Therefore, sine 2t is bigger than 2 over pi times 2t, which is 40 over pi. So when I take minus, I get the exponential is strictly increasing. So this function here is less than exponential of minus r squared times 40 over pi. Okay, so I get minus 4r squared over pi t. Now, here this integral is of course computable, because we know an antiderivative of the exponential. Okay, it's exponential of the same thing divided by minus 4r squared over pi. So yeah, so I get this estimate. Maybe there's an error, I think, because I have r here and pi minus pi over 4r squared. So there is 4r, not 4r squared. Okay, because there's the r here. So this is just the value of the integral, but there is, you have to multiply by r. But anyway, it's not really important, because now as r tends to infinity, this tends to 0, even if I had r here, right? And of course, this is something positive, because the exponential is less than 1. Okay, so I can write it as 1 minus, okay? Okay, so now I proved what? I proved that the second integral that I cannot compute explicitly tends to 0 as r tends to infinity. And this is all what I wanted. Okay? So, therefore, this is what I said. So the second integral tends to 0. And finally, if you put everything together, this is the first integral, this is the second integral, and this is minus the third integral. So the equation is the first integral plus the second plus the third is 0. Okay, but the third was minus this. Okay, so this is just an arrangement, because by the result of complex theory tells me that the sum is 0. Okay. Now I'm ready to let r tend to infinity. When I let r tend to infinity, I get by definition the integral from 0 to infinity of cosine t squared plus the same thing for sine t squared. This tends to 0, and this tends to the integral that we know is radical pi over 2, as you observed. Okay, so, and from this we deduce by separating the real and imaginary part that both integrals have the same value, which is radical pi over 2 radical 2. Or if you like, 1/2 radical pi over 2. Okay, these are called the Fresnel integral, and they are important in optics. So this concludes the second exercise and illustrates a typical strategy of computing real integrals by complex variables methods. Okay. Now, third exercise, very similar. I will not draw a figure. You draw it, because in the exam I may just give you the loop by giving the pieces, for example. So I just describe it verbally, and then you have to draw. Okay. So we have a rectangle of vertices minus r, so horizontal, r plus pi I omega, and minus r plus pi I omega. So this is the rectangle of this one. So you draw it. So by integrating the function e minus z squared along this loop and letting r tend to infinity, compute this complex integral of a real variable. And this has a name. You will learn soon that this is the Fourier transform of e minus x squared by definition. And of course, there are other ways to compute this Fourier transform. But this is the way using the complex variable method. Okay, so like the second exercise, the function that I need to integrate is holomorphic on the whole plane, which is convex. So it has an antiderivative, and therefore the integral over any loop is 0. And now, as in the previous exercise, we just have to split the integral along paths composing the loop. There are 4 of them. The first one is the horizontal line joining minus r to r. So a parameterization is, of course, gamma 1 of t equal t, and therefore gamma 1 prime equal 1. Now, on the second vertical side, the real part is constant, is r, and the imaginary part varies from 0 to pi omega. So once again, omega is real. It's constant. And so the derivative is I. Now, the third integral is the opposite side of the horizontal. It's also horizontal. Here, y is fixed, it's pi omega, and t varies, but not from minus r to r, from r to minus r. So once again, pay attention to the orientation. When I write this, it means that when I later compute the integrals, I have to put the integral from r to minus r and not from minus r to r. Okay, and then the last one, you guessed, the real part is fixed, the imaginary part varies from pi omega to 0, once again, with this orientation. Okay, so we have 2 unconventional orientations, but they are useful in computing integrals instead of writing pi omega minus t or, okay. Okay, so now let us evaluate each integral. There are 4 of them. I call the first one I1, second one I2, I3, I4. Okay, now the first one, straightforward, is the integral from minus r to r of e minus t squared. Just replace gamma 1 by t. Gamma prime is 1, so this is straightforward computation. And we know that this converges to radical pi as r tends to infinity. Okay, so don't try to compute it. Second one, we also have an estimate. You cannot compute it explicitly, but you can do an estimate. So if you go back to the definition, it's the integral from 0 to pi omega, and replace z by its value and multiply by the derivative, which is I. And now if you expand this, you get r squared minus t squared plus 2rit. So but you have a minus here. So when you do the algebra, you will see that we have e minus r squared in factor, so I can put it outside, and the function is inside is of this form. Now this is all what we need, because now when we take the modulus of this constant is itself, because it's positive, and the modulus of the integral is less than the integral of the modulus, which is once again et squared, because the modulus of this part is 1, as you should know. And now we are done. This is, of course, it contains et squared, which is unbounded, but the integral is between two finite bounds. So this is just a constant depending on omega. Omega is fixed in this reasoning. So this is just a constant depending on omega. So when r tends to infinity, all this tends to 0. Okay. And once again, I don't need to compute this integral, which is not computable with the function that you know. So the first one tends to a constant. The second one tends to 0. Third one, same thing, straightforward. If we do the algebra, we expand here. We can put the constant, which is e pi squared omega squared, outside. And now it doesn't tend to 0, unlike the second one, because this is a constant, okay? And yeah, I just put minus because it's from r to minus r because of the orientation. Okay, so pay attention to this point. And now this integral actually is what? What happens when r tends to infinity? This, by definition, is the integral from minus infinity to infinity of this function, which is by definition the Fourier transform of e minus t squared, which I call g omega. You write it f hat of omega. Okay, so I3 converges as r tends to infinity to my unknown number. Okay, so I don't do anything here more than that, but I have to recognize that this is the integral I'm searching for. Okay, now the last one, like the second one, if you do the computation, you will convince yourself that it tends to 0 for the same reason, actually. Actually, yeah, I should have put the modulus inside because the modulus of the integral is less than the integral of the modulus. Of course, we can change the the orientation. So, but at any rate, you can convince yourself that this is just a constant. The integral of the modulus is a constant that depends only on omega. This term has modulus 1 once again. So the fourth, in conclusion, the fourth integral also tends to 0 as r tends to infinity. Okay, and now I put everything together. I have the sum is 0, and if you let r tend to infinity, first one converges to radical pi. Second one and fourth, second and fourth converge to 0, and the third one converges to minus the Fourier transform times this constant. Okay, and therefore I get that the Fourier transform is radical pi times e pi squared omega squared. Okay, so this is very similar to exercise 2. And this concludes exercise 3. The last exercise, we asked a lot of such questions in the exam. So we take the unit circle, and we have to compute exponential of 1 over z over the unit circle, and then answer if there exists an antiderivative of e to the 1 over z. So does there exist a holomorphic function from c star to c whose derivative is e1? So otherwise, the question is, Does E1 over Z possess an antiderivative on C star? Okay, so we first start by recalling the formula for Ez and the fact that conversion is uniform on all compact subsets of C, as we observed earlier. And now we just replace Z by 1 over Z, so we still have this expansion of E1 over Z. And since convergence of this series is uniform on compact subsets of C, then convergence is also uniform on compact subsets of C star, as you may check. Okay? Because if Z lives in a compact subset of C star, then 1 over Z lives in a compact subset of C. Okay? So just if convergence is uniform here, then it's uniform here. Okay? And by the way, this is in chapter 3, this is called the Laurent series of E1 over Z because about 0, because this is not holomorphic at 0. Okay, so it has, but anyway, so now if you follow the hint, we have to integrate term by term. And this is why we invoke the notion of uniform convergence, because we can integrate term by term if we have uniform convergence. Okay, so we can interchange sum and integrals. So the integral of E1 over Z is the integral of the first one plus the integral of the second plus the integral of the third and so on, because the circle is compact in C star. Okay, now we observe something actually, that the integral of 1 along the circle is 0. Why? You can do it directly because it's the integral of dt times IEIT. This is first. Or second method, you may notice that 1 has an antiderivative, which is Z, and by Barrow's rule, the integral over a loop is 0. Now, the second one, the integral is not 0, so we leave it. The third one, also 1 over Z squared or 1 over 2Z squared has an antiderivative, right? And the derivative is given by constant times Z minus 1, okay? So by Barrow's rule, again, the integral of the third term is 0, and similarly for other terms, okay? Now, the term 1 over Z is special in complex variables because the 1 over Z does not possess an antiderivative on C star. It possesses antiderivatives on smaller parts of C star. So the log that you learned, the logarithm that you learned in first course is actually defined on C without R minus and not on C star. Okay, so we know that an antiderivative of Z to the n is Zn plus 1 over n plus 1, provided n different from minus 1. So all terms possess an antiderivative. This is one way of seeing things. So all terms possess an antiderivative except this one. So by Barrow's rule, the integral is 0. Okay, so you are left just with this integral over 1 over Z. If you don't believe me, you can do a direct computations actually, because you have negative powers of Z. So when you replace, you'll get E minus n int, and then times the derivative, and you can directly compute this on the unit circle actually, and you'll convince yourself that you get 0. So there are two ways of seeing that all terms have 0 integrals, either by a direct computation, I will not do it, you do it, or by invoking that the terms possess an antiderivative, and therefore the integral over a loop is 0. So in conclusion, the integral of E1 over Z is just the integral of 1 over Z. Okay? So, and by the way, the coefficient of 1 over Z here, it's 1, has a special name. It's called the residue of the function at 0. Why? It's called the residue because it's the only surviving terms when we integrate. When we integrate, all terms vanish except this one. Okay? So this is a technique that we shall return to in chapter 3. Okay, so in conclusion, the integral I'm searching for is just the integral of 1 over Z, which we already computed in the lectures, which is just 2 pi I by a direct computation. Okay? And therefore, the integral is 2 pi I. Now we can answer the second question by reason by contradiction. If this function E1 over Z possesses an antiderivative, capital F, then by Barrow's rule, the integral should be 0 because we are integrating over a loop. but the integral is not 0. Therefore, this function has no antiderivative on C star. It's a very, very simple question that tests your understanding of the course. We always ask such questions in the exam. Okay, so thank you for your attention and see you next time.